Hello students, welcome to Math 1325 Applied Calculus. Lesson 0 covers preliminaries only, so if you feel comfortable, just skip it all together and go directly over to Lesson 1. That's okay, and I'm not going to stop you. Now, if you want to start from Lesson 0, listen carefully here. Everything here is Lesson 0 is a review, and some of them are coming from really old materials. You don't really have to go through them all. You can select anything, you can skip anything and do it in any order. So keep that in your mind and let's begin. Let's go to section 1, Algebraic Preliminaries 1, and let's do subsection 1.1 in this video. We're going to do the next subsection in a separate video. Sets and elements. I hope everybody is already comfortable with the idea of sets and elements, but in case there are some people who are a little bit hazy about those, here we go. What do you mean by set and element? As you can see in this kind of expression, a set consists of list of some elements, 3, 6, 9, 12, and so on. I hope you see the pattern. And these things inside the set are called the elements. And put all those together, that's called a set. So something is inside a set or not, or something is an element or not is explicit. There's no gray area, it's yes or no, nothing else. If you have that kind of relation, then you can say this is a relation between set and element. In this case, any positive multiples of 3 is a member, an element of the set S, otherwise it's not. Now that's one way to express a set, by taking a list of all the elements, or at least a pattern of it. Another way is to explicitly write down the condition. This thing is called the set builder expression. This one is list expression. So this is called the list expression. The list expression of the set. And this one is called the set builder expression of the set. So X is a positive multiple of 3, 3, 6, 9, 12, 15, and so on. Everybody can see these two equivalent, whether you use the list expression or the set builder expression. Now, we use this kind of expression that looks kind of like an E to denote an element, and then remove the middle bar from that E expression, and that's called a subset. For instance, 27 is a positive multiple of 3, so that's an element. 3 times 9. 34, on the other hand, is not an element, so expressed like this, using the E notation, and E, but slash, no. Now, if you put a number of elements and form a set, then you can compare the new set with the previous set S. If all the element here is a member of this set S, then this thing is called a subset. And 3 is an element, 30 is an element, and also 33 is an element. Let's see, 42 is an element, 96 is an element. Okay, all right. So we have a subset. Now, here, 33 is okay, but 2 is not. So this is not a subset. And I don't care how many I have over here. I don't care how many I have here. If there is only one element that is not member of this set S, then this thing is not a subset. Now, if I cast this one out, then of course this becomes a subset. But of course, that's not where it was before. Okay, so much for sets and elements. Now, another expression that everybody has to become familiar with is a set of numbers. We use these expressions, NWZQRC. We use the double stroke font, the set of natural numbers, also known as the set of positive integers, 1, 2, 3, 4, 5, 6, and so on. Set of whole numbers, 0, and 1, 2, 3, 4, 5, 6, 7, and so on. Now, set of all integers, not just positive integers, but also negative integers and also 0. So not just 0 and 1, 2, 3, 4, and so on, but also -1, -2, -3, -4, -5, and so on. Now, all these are discrete. One, and then the next, and then the next, like that, either to the left or to the right. Now, this one is very different. Set of all rational numbers. What is a rational number? It's an integer over integer. Let's see. So that is okay. And then the set of whole numbers is this kind of thing. And then this one is gonna be, let's put some space. There you go. Those are a set of natural numbers, whole numbers, and integers. See the pattern here? Okay, all right. And please note that they're all discrete. Now, Q is a little bit different. Is this. So it's a set of fractions, integer over integer, where the denominator is non-zero, of course. If the denominator is 0, you cannot make a fraction, and that's undefined. So not just any fraction. And if you have something like square root of 2 over 3, then so this is not a rational number. You have a fraction, yes, but the numerator is not an integer. How about this? Is this an integer? Is this an integer? Well, this is not written in integer over integer form because numerator is 2/3, not just an integer. But the answer is yes. It can be written as an integer. So 2/3 over 5 is actually, if you simplify, multiply 3 to both numerator and denominator, you end up with 2 15, and that belongs to the set of all integers. I mean, set of all rational numbers, integer over integer. So that's what this set of all rational numbers Q is. All the fractions of integers. Of course, denominator cannot be 0. Denominator is 0, then the fraction is undefined. So another thing that is interesting about this Q is the set of all rational numbers is not discrete anymore. All these are discrete. You have a certain number, we have the next number, there's a gap. One number, and then the next number, gap, and then the next number, gap, and then the next number, gap, like that. Q is different. I mean, between any pair of rational numbers, you can find at least one, consequently infinitely many rational numbers in between. See, for example, P and Q are rational numbers, then you can find at least one rational number in between. Simply take the average. And this number, the average, is between P and Q. Is this here only one? No, not really. If we can take average of this and P, and then you have another, the average of this and Q, and then you have another, and so on and so forth. So one number in between any pair of rational number, consequently infinitely many. So there is no such thing as next highest rational number. This is not discrete. So this is called, I'm not going to use the term dense. So these are discrete, and Q is not. The set of all real numbers, the property of real numbers is this. Set of all real numbers fills up entire number line, no gap. So from here, from the set of all real numbers, you can combine algebra and geometry together. And not coincidentally, that's why this is a starting point of everything. We can do graphs, and we can do geometry. Everything goes to the set of all real numbers. As for the set of all complex numbers, we dealt with some of those in limited basis in the algebra, but in this class, in applied calculus, I don't think we'll ever deal with any complex numbers, so let's not worry about it. So our default is R. We start from there if nothing is explicitly mentioned. And speaking of, part of those real numbers, these are important intervals. All the real numbers in between A and B, including A and B, the endpoints. So please note that semi-inequality corresponds to bracket. Strict inequality corresponds to parentheses. Here, if we do not specify these belong to R, will that matter? No, not really, because our default is just R, even if it is not explicitly mentioned. But of course, it's better to mention it explicitly. So let's go back to where they were. And please remember these expressions. We can have all those intervals. In any case, if you have strict inequality, that's parentheses, and semi-inequality, that's bracket. You can have half open, half closed like that. All those are interval expressions. I guess that's it for set notation, subsection 1.1.